السيدات والسادة المحترمون، مع حفظ الألقاب والمناصب، السلام عليكم ورحمة الله وبركاته. برعاية السيد رئيس جامعة القادسية المحترم أستاذ الدكتور كاظم الجبوري، وإشراف السيد عميد كلية الهندسة أستاذ مساعد الدكتور علاء الموسوي المحترم، يقيم قسم هندسة الطرق والنقل في كلية الهندسة جامعة القادسية الندوة علمية تحت عنوان تصميم الخرسانة المسلحة القائم على الديمومة في ظروف بيئية قاسية، رؤية شاملة لمشروع هورايزن 2020. يحاضر فيها البروفسور ليبيراتو فيرارا، وهو بروفسور في التحليل والتصميم الإنشائي قسم الهندسة المدنية والبيئية جامعة بوليتكنك في ميلانو إيطاليا، ومدير مشروع ريزيلينس ومشروع سمارتنجز الخاصين بتطوير الخرسانة فائقة المقاومة. So now we will proceed in English version. Ladies and gentlemen, on behalf of President of University of Al-Qadisiyah, Professor Kazim Al-Juburi, and the Dean of the Engineering College, Assistant Professor Ala Al-Musawi, I would like to welcome you all in a Smart Mode seminar organized by Roads and Transportation Engineering Department at University of Al-Qadisiyah. The speaker today is Professor Liparato Ferrara, is a professor of structural analysis and design at Department of Civil and Environmental Engineering at Politecnico di Milano. Professor Ferrara is the coordinator of the project Resilience. This project has received funding from the European Union Horizon 2020 Research and Innovation Program. The main goal of the project is to develop an ultra-high durability concrete and a durability assessment-based design methodology to improve the durability of the concrete structure and predict their long-term performance under extreme aggressive exposure. On behalf of the University of Al-Qadisiyah, I would like to thank Professor Ferrara for his opportunity. And as a matter of fact, he agreed to give this seminar in a short. It's busy for him with all graduations and open week events. So without any further ado, we welcome Professor Ferrara to give an overview of the project, and we will allow 10 minutes after the presentation for the question and answers. So Professor Ferrara, the virtual stage is all yours.
Okay, you can hear me?
Yes.
Okay, good evening, everybody. Actually, my computer seems blocked. I don't know. Okay. Let me check, Salam. Let me disconnect and restart because I cannot do anything more. Sorry, just a moment.
Okay, fine.
Okay, good evening, everybody. Can you all hear me?
Yes, Professor.
Okay, perfect. Sorry for this inconvenience, but it's something that we're getting more and more used in these times where the internet and Wi-Fi connections are becoming more and more heavy. I have to thank you, Salam, and to thank all of you and all the colleagues for having organized. For me, it's really a pleasure to be with you this evening and to tell you about our resilience project. Now I'm trying to share my screen.
Yes, it's obvious, Professor.
Okay. You can see it?
Yeah, but it's
okay.
Clear.
So we can start. Thanks again. And it's really a pleasure, as I was saying, to be with you. Well, as Salam, I am very, very happy and proud to have him as PhD student in my group. As he said, the topic of an overview of the Horizon 2020 project Resilience, which is focused on the concept of advanced and based design of reinforced concrete structures exposed to extreme aggressive environments. Let's try to frame not only the project, but let's figure and in a wider, broader view, our work as engineers as of construction. As a matter of fact, we know that we are in desperate need world of transportation infrastructures. And probably no more than now, in a period in which we are forced, most of the world, to stay inside, we realize how important are transportation infrastructures, because they connect people and countries and cultures, and they transport. And as a matter of fact, every 1% of the gross domestic product that you invest in infrastructure in 4 years generates 1.5% growth in the GDP. Coastal protection, well, I focus at this on the European situation, but Europe has 66,000 kilometer coastline, 3 times as much the coastline of the US. And the coastal defense infrastructure market sums up to 660 billion euros a year with a foreseen growth of 4%. Well, obviously, these figures are before the COVID crisis. But as a matter of fact, there is an important issue that we have to consider when we speak about coastal protection, which is also the effect of climate change with an anticipated sea rise of 1.7 millimeter per year. And dealing with this, we have initiatives worldwide to promote the growth of clean energy production, offshore wind energy, ocean energy, geothermal engineering, and promoting blue growth, the growth of the economy related to the sea. Because we know that 70% more or less of our planet is made of water, but only 5% of our economy develops in it. And the land is depleted and the land is exhausted. So this could be a resource for sustainable development as well. So which is the scenario in which we are working and in which we shall be working? I put this figure here. It's quite, well, for me, it's an amazing building designed by Santiago Calatrava and is in the harbor of Rio de Janeiro. It's quite a new building because it's part of a redevelopment project of the harbor area in Rio de Janeiro in Brazil, which was done for the Olympics in 2016. And this is a museum, and it's called the Museum of Tomorrow. So inside there is a terrific exhibit, I would say, where, you know, they try to force us to think how the world will be in the future. And the scenario is that nowadays, 55% of the world population lives in cities, lives in urban areas. And if you look at high-income countries, up to 80% of the people live in urban areas. And every year, about 1% of the current world population, more than 1%, because it's 75 million, they move from the countryside to the cities. And in 25 years from now, 2 over 3 people on planet Earth will live in the city. But when I visited this museum about 2 years ago in summer 2018, I was hit by one of the panels in the exhibit that you can see here in the bottom left, in bottom right, sorry, where it's written that humankind has become a geological force. So we have acquired such a power that we are able to shape the planet like a geological accident or geological event, an earthquake, a landslide, a hurricane, or whatever, is able to do. And which are the consequences of this, for example, on structures, on concrete structures? Well, for example, we have, because of climate change, we have increase of carbonation-induced corrosion, because in our atmosphere, the CO2 content increases and there is global warming, which also promotes carbonation. We have, because of increased seawater salinity and acidification and increase of sea temperature, an increase of chloride-induced corrosion. And because of extreme events, we can also have an increased physical wearing of concrete structures. On the right of the slide, you can see the results of a study which was performed some years ago by a research group of the University of British Columbia in Canada, which shows in a mega city like Mumbai, like a building which has been built in 2000 had an expected service life at that time of about 65, 66 years. But due to the climate change, a building built in 2030, will have at that time an expected service life of 56 something years. And if you see on the same buildings how the service life evolved with time, because the climate conditions change, you can see that also for a building built in 2000, after 15 years, because the study then took the data of 2014, the expected service life already reduced of about 10 years, so to about 57 years. And the same and even faster decrease will occur in the future. Well, as a matter of fact, this is just one of the examples. And we know that for structures which experience these aggressive conditions, we have in the codes prescriptions on how to design structures which can guarantee a minimum expected service life. So for chloride-induced corrosion, I use here the notation and the symbols and the prescriptions of the Euro code, which is the standard and the code I am used to. So chloride-induced corrosion, we call condition XS. So we have some prescriptions about the maximum water cement ratio, minimum cement content, and minimum compressive strength. And if we have structures exceed attack, we have different prescriptions according to the severity of the accident. But as a matter of fact, if you look at this table, hardly you can realize there is a performance here. These are prescriptions which are mainly barred to achieve a minimum level of performance. But also structures built respecting these prescriptions have this situation. These are structures which are really not older than 10 to 15 years, so which were built, designed and built according to the prescriptions. The left is a harbor dock in Morocco, and the right is a structure in the harbor in Spain, in a harbor in the Mediterranean coast of Spain. And you can see very damaged spots, which probably occurred in the case of the harbor, for example, due to the repeated hitting by the ships, by the vessels. But also because one thing is what we design, another thing is what we construct on the site. There are several variables intervening between them. These are some other pictures which are strictly referred to our project Resilience because are a structure on which we are trying to intervene in some way. This is a cooling tower in a geothermal power plant. In the cooling tower, the water, which has to be cooled down before being reinjected in the ground after the geothermal process, well, it contains a lot of sulfuric acid and sulfates, so it really corrodes the concrete because of the reaction which happens. And you can see the severe state of damage in which these structures are. And also on the right, you can see that the beam was repaired. The top part is evidently new, but the degradation with the production of heteringite and other kind of expansive products continued also after the retrofitting of the structure. Well, as a matter of fact, this poses also the problem that we have to consider not only how durable and how long durable is a structure when it's newly built, but also we have to consider how durable will be a retrofitting. So how long a retrofitted structure will last. And according to a survey made by this European project about 10, 13 years ago, 50% of the repaired concrete structures once again after the repair. And 1/4 fails in the first 5 years after the repair. So we really need to go for an urgent need of profoundly rethinking the concept and design processes for new and repaired structures in aggressive environments. Also in view of the challenging demands. So what is the performance that we have to ask to our concrete? The first performance that we ask to concrete is the strength, is the compressive strength. But nowadays, we can really effectively make very high concrete strengths. 60, 80 megapascal are quite common, 100, even more. And also, we have become very, very good in taking the best, in exploiting at best, the strength capacity of our binders. Because you can see on the right graph, to produce a 100 megapascal concrete, well, we have to use the effectiveness of the binder is that we need 5 kilos per cubic meter per megapascal of strength of binder in the mixture. Whereas to produce a 20 megapascal concrete, we use between 10 and 15 kilos. So these high strength mixes, is true that they contain more cement, more binder, but it's also true that they use the binder 2, even 3 times better than in ordinary concrete. But the other thing is that, well, do we really need higher and higher strength? And can we really do better than what we are currently doing in terms of efficient use of the binder to get the strength? Or shall we look to some other performance from our materials and from our structures? So I tried to think a little bit out of the box. I went to a literature book, which I read when I was a high school student, by an Italian writer who died more than 30 years ago. I loved him quite much. And it's called American Lectures because were 6 lectures that Italo Calvino, this is the name of the writer, was supposed to deliver at Harvard University in the fall of 1985, and he died barely 15 days before leaving to the US. And he gave a subtitle to this book, 6 memos for the next millennium. Which are these 6 memos or 6 keywords? Well, he wrote this: lightness, quickness, exactitude, visibility, multiplicity, and consistency. And so I tried to say, okay, how can we decline, how can interpret these words from the structural engineering point of view? So lightness could mean, let's guarantee the same structural performance with using less material. Quickness, faster construction. Exactitude could mean, let's optimize the structural use of the material. Let's try to think in a metamaterial framework. So let's try to not think from a material and see what performance does he have and design accordingly, but let's try to reverse the process. Let's try to see which is the performance that we need, the level of performance that we need, and let's try to design a material which guarantees that performance and that level of performance. Let's use structural shapes which really match with the function. Let's try also to think of something which does not replicate the same beam and column scheme. Let's try to think of materials multiplicity, materials that are functionally graded, that have non-conventional functionalities and properties. And let's try to think all of this in a consistency framework, in a holistic approach, which combines the process and the performance. Well, this was the initial framework in which 14 European partners, you can see here, the law, we grouped together in order to propose for a project European Commission. Well, we had previous interaction with 6 universities, and we had research collaborations for a long time before, and industrial partners were related to different of us. But most of all, the important thing is that the industrial partners, and this is one of the keys of this project, they cover the whole value chain of the construction industry. We go for material production, to precast concrete, to engineering consultancy, to large end users, because Enel Green Power is the largest Italian and European producers of renewable energies. So it's a large end user. And we have precast concrete, engineering, construction firms, infrastructure and construction companies. Well, this is the logo of our project, and the title, well, we focused in the title on coastal defense and green energy service infrastructures through enhanced durability, high performance, fiber reinforced cement-based materials. So the project is now in its second half, because we started at the beginning of 2018, and our goal is to develop a ultra-high durability concrete and the methodology for durability assessment based design for the design and construction of structure under extremely aggressive environments, because we want to improve the durability and predict the long-term performance. Well, so which was, our starting point? Well, our starting point was ultra-high performance fiber reinforced concrete. This is, a movie in our lab, but by master thesis students. I don't know if you can also hear the soundtrack that a colleague of mine put under this movie. It's music by Bruce Springsteen, and its title is Tougher Than the Rest, because we all know that these ultra high performance materials, they are extremely important for their enhanced toughness, fracture toughness. Where do we want to use these materials? Well, we have used it because these pilots are ready. Some of them are already in place. Some of them just need to be put into place because we had some delays due to the COVID crisis, into 6 pilots. 2 of them are in Italy and are 2 basins in a geothermal power plant. 2 of them are in Spain. It's a water tower floater and a raft for mussel farming in the Mediterranean Sea. Another pilot is in Ireland, it's a floating pontoon. And another pilot, you can see the picture here in the right bottom of the slide, is an existing building. It's a water tower in the harbor area of Valletta in the Malta Island. So these are different structures in different exposure conditions, because we go from acid attack to chloride attack in different temperatures, because the Mediterranean is different from the North Sea with the wave motion. Or also we have the airborne chloride salts, like in the case of the existing structures in Malta. And we used these 6 pilots, we devised and designed them because they are related to 3 specific cutting-edge sectors of our economy: green energy, as we were saying in the beginning, blue growth, and architectural heritage conservation. And we started assigning the performance requirements. For each of these structures, we have different requirements in terms of strength, in terms of workability, in terms of presence or not of fibers, if we wanted to use conventional reinforcement, which was the availability of constituent materials in terms of cement, in terms of supplementary cementitious materials, and so on. And also, for example, to cast a new structure, you need a consistency which may be different from the one that you need to retrofit the structure. So we worked with self-compacting materials and also with textile thixotropic materials. We did not use the same material everywhere, not only because of the components which were available in different ways in different countries, but also because the requirements was different. So our key idea is that you do not have a unique UHPC, UHDC material, but you have a solution-based, a scenario-based material. So we will focus in the next on the material that you see here framed in red. That is the one we work directly on with my group at Politecnico di Milano for the pilots which are located in Italy. And we started characterizing it. We casted some beam specimens, thin beams, and we tested them in bending, and we obtained multiple cracks. You can see on the scheme, but you can see also here in this figure on the left, top left, you can see how many cracks were developed in a 20 centimeter space. Then from the results of flexural tests through the laws of fracture mechanics, we were able to identify the constitutive relationship in tension, which was used in the design. And we also developed a specific test methodology, which we call a double-edge wedge splitting test, to directly identify this law. Because if you make a bending test, then you need a back analysis to identify the law. Whereas we need something which was fast and effective. So we developed this test, which is basically a modified Brazilian splitting test. We introduced the notches to localize, which is also sensitive to the alignment of the fibers. And so we hypothesized that we calibrated experimentally and numerically. And we hypothesized that, well, we believe that this test gives us straightforward the tensile stress crack opening constitutive law of the material. Is this true? Simply pick up the results of this test and use them to back simulate the results of bending test. And so you can see that we have the purple curves in the right graphs are the modeling, and the black are the experimental data. If you test a thin beam, the prediction is on the lower bound, because in a thin beam, the fibers are aligned in the thickness of the specimen, so they work in their best way. If you test a deep beam, the alignment of the fibers is random, so our prediction was on the upper bound. Well, this was, how to say, for sure, we were happy about these results. You can say, well, but why are you happy if you get, in one case, a lower bound, which may be on the safe side, and in the other case, an upper bound? Well, because these materials, one of the specific characteristics is that we want to use them in order to reduce the quantity of material that we use. So we will design our structures in order to have thin elements, much thinner, and you will see, than what you will have in conventional concrete. So in this case, the prediction is really up. And so we started with the design of a basin to contain the water. The current solution for this basin, which is in reinforced concrete, to contain the water in geothermal power plant. The current solution designs the walls of this basin 40 centimeters thick, just for the sake of durability. In our pilot, we wanted to test also some advanced solution in terms of self-healing, and we designed and built our walls 10 centimeters thick. And we made an elastic stress analysis. I have to acknowledge my colleague, Professor Bamonte, who coordinated this work. And we extracted the tensile stresses on the inner face and on the outer face. You can see that on the outer face we have some tensile stress, very low, 0.7 Newton per square millimeter, a little bit higher just at the clamped edge on the bottom in the inner side. But anyway, the tensile strength, 3.1 Newton per square millimeter, is close to a flexural tensile strength of a regular concrete. And considering that you will have ordinary minimum steel reinforcement, this level of stresses is surely coherent with the design. Then we said, if we use our ultra high durability material, let's see how low can we go, how thin can we go. And we were able to design specimens, not specimens, but in this case, structure, the walls of the basin, as thin as 6 centimeters. And well, the level of stress is higher. Well, on the other side, it's lower than 2 Newton per square millimeter. Here on the bottom, you can see that it's a little bit less than 9 MPa. But if we compare this level of stresses with the constitutive curve of this material, we can see that we are in these 2 dots. 2 megapascal is still on the elastic range. And well, 9 megapascal, if you continue with the elastic initial stiffness, you will go out of the constitutive relationship. But you can see that 9 megapascal is still in what is the strain hardening behavior regime of this material. It's a regime of behavior of this material where you form multiple cracks. Each one of them is very, very narrow, very tiny open. So in this case, there are no problems in withstanding this level of stress. Remember that we moved from 40 centimeters in the original solution to 6. So there is a saving of quantity of material of more than 6 times. And we have no reinforcement at all, but we have the fibers inside this material. According to the mixed design that I showed in the previous slides, there are 120 kilos per cubic meter of steel fibers. So this is ultra durable concrete that we designed to use, strain hardening fiber reinforced cementitious material with functionalizing micro and nano scale constituents, because in these materials we added crystalline admixtures for self-filling, we added alumina nanofibers, cellular nanofibers, and nanocrystals. For sure, sorry, we can obtain a higher performance. For example, if you compare with the conventional concrete, our material will be a curve B, and the conventional solution will be curve A, so we are higher. Which means that we also pay a higher cost. We will see later probably how much higher. But a higher cost at the time of construction may not necessarily mean a higher life cycle cost, because higher cost and the higher performance now may also mean that you have a longer durability, and so you will need an intervention later in time, adding up additional extra cost later in time than what you will need for conventional concrete solution. Well, so we tried to incorporate into these materials some self-filling admixtures. So this stimulate the growth of hydration products and seal the cracks. And for example, we performed some permeability tests just to verify the flow of water. And you can see the black curve on this graph immediately after the cracking, and after 1 or 3 months, how the performance decreased, the permeability, sorry, the flow of water decreased because of the closure of the crack. And we could observe the crack closing. These are some results not published yet, which were obtained by my colleague, Professor Alba Peled in Ben Gurion University. The crack closes after just a few months, and you can see the crystalline growth inside the crack, which reconstitutes the true crack continuity of the material. And we also observed, you can see other images of the cracks closing, and we observed how under repeated cracking and healing cycles in this graph, you have the purple curve, the green, and the red. Every time we pre-cracked the specimen, we healed for 1 month. So when we restarted, the material was able to guarantee repeatedly the same level of performance. And we also observed that it's not only closing the cracks, but also at the level of the fiber matrix interface, there is a position of the products along the interface, which really improve the fiber matrix bond and enhance the toughness and the performance of the material. So we wanted to go further, and we also went into the domain of nanotechnology. This graph for people working in this field is very well known and shows the ratio between the specific surface area, which is also the reactivity of the particle, versus the particle size. Well, we used alumina nanofibers. You can see here a nanograph showing them and the data of their dimension, or nanocellulose fibrils and crystals. These are products of some of our partners in the resilience project. So we used them very, very specific and low dosages. 0.25% by weight of cement, the alumina nanofibers, for example, and 0.15% by weight of cement for the cellulose products. Well, what does it mean? 0.25% by weight of cement times 600 kilos of cement per cubic liters means that we need 1.5 kilos per cubic meter of alumina nanofibers. Seems a very low quantity. But as a matter of fact, the problem is the dispersion of these nanofibers. On the market, which is not really, for this product was not the construction market, but was other industrial applications, these nanofibers came in a suspension at 2% solid concentration. So in order to have 1.5 kilos of nanofibers, you need 75 liters of suspension. But in our material, if you look here in the mixed design table at the line water, we had only 200 liters of water. If 75 of them have to go with the nanofibers, you will never be able to mix this material because your mix will be very, very stiff. So with the companies, we developed a process to produce a 10% solid concentration. The thing is not only making a denser suspension, it's to disperse adequately the fibers at that suspension. So we were able to successfully produce this more concentrated suspension. These are some examples that we also made with the cellulose. And this is on the bottom left, you can see a picture of the very dense cementitious mix that we were anyway able to successfully mix. So we said, okay, let's try to see how this nano addition work. And we tested in the beginning the compressive strength, curing the specimens in a climate room or under the geothermal water, which we kept from the plant where we were going to build the pilot. And we were a little bit disappointed in the beginning because the results you can see here showed us that the effect of the nanofibers were not so good, because the reference mix is the gray column, especially if you look on the long term. The reference mix is the gray column, the blue curve is with alumina nanofibers, the green and red, sorry, are with the nanocellulose product. You hardly observe any significant change. But this is the reason, because I said compressive strength may not be performance that we look for. When we look into the flexural strength, here we really saw an improvement, especially in the long term, and also especially in the case of the curing under geothermal water. Because, you know, when we make characterization of our material, we cure the material in ideal conditions. But if we have to build a structure which has to serve as a basin for geothermal water, we cannot wait 28, 56 or whatever days curing in ideal condition. The basin shall be used immediately. So it will cure under the aggressive water. And this is where the nanofibers did really their job. So we have to look into the right performance to understand the effect of these materials. Well, what is this effect due to? Well, for sure, you can see that there is a poor refinement because the reference mix is the blue and the mixes with alumina nanofibers or nanocellulose are the green and red curve. Also, this resulted into a reduction of the shrinkage. And this reduction of the shrinkage, you see, it lasted, we tested up to more than 6 months. This reduction is maintained constant over time. And we see here some micro and nano picture. There is really a reinforcement at the structure of the crystalline matrix. These are the alumina nanofibers. And these you can see here in the right figure are some of the other products. And you can see these are the nanocells. See how they also serve as nuclei for dehydration. The foam, what appears like foam, are the hydration products of the cement around the cellulose particles. Also because the alumina nanofibers have some hydroxyl groups on their surface, so they are hydrophilic as well. And the cellulose absorbs water and release them on demand. Also, we made an extensive characterization test, and you can see how the healing was improved, because in this graph, you have the efficiency in recovering the impermeability versus water penetration and the closure of the crack. And you can see that the gray points are the reference mix, the blue are the alumina, the green are the nanocellulose, and the red as well. So the nanoparticles always bring you higher and higher with the efficiency of the self-healing process. This is, I'm happy to say, because these are the results of a master thesis which was discussed yesterday, and the student was very well rewarded for his work. So in the end, we said, okay, how can we better exploit these results in designing a new solution for the basin? So we thought of designing the basin in a precast way using precast slabs, and the slabs shall be cast horizontally, then lift vertically and fixed. You can see here in the scheme, I don't know how much clear it is, but there are some buttresses, some columns which stiffen the wall. Well, we were able to reduce the thickness of these walls to 3 centimeters. And where you see the missing part in the top figure and the 3 squares here, actually in the pilot that we constructed, those 3 slabs are 2 centimeters thick. Well, obviously, the stress increases because you go to 4.5 and even to 11, and 11 is something which is outer of the material capacity. But first of all, it's very, very localized at the border, at the boundaries of the slab. But the other thing is that this is an elastic analysis, and we know that this material really work in post-elastic regime. So this is a calculation to which also Salam Al-Obaidi participated with Professor Bamonte, and we have submitted the paper to a conference in September. We used the yield line mechanism approach to predict the performance. And we realized that even with 2 or 3 centimeters thick, our slab was safe, and we were able to withstand also a surcharge weight much higher than the height of the wall. Well, actually, also, this solution brings you really advantages in terms of the 7 indicators of sustainability, because you can see, due to the fact that we use an extremely reduced quantity of material, and the fact that the material is self-healing, so has a longer service life and lasts longer, we have a reduction in acidification, eutrophication, global warming, all the other indicators. Well, we can go from 11% reduction in eutrophication, which is not exactly the field in which construction industry is more dangerous, but acidification we reduce 45%, and the use of fossil fuels we reduce by 73%, because we know that if we use lower concrete, we use less cement, we need to produce less cement, and this is one of the most energy consuming and CO2 emitting industrial operations. Also, we have started working on some kind of durability design approach. What does it mean? Well, we want to incorporate durability into the prediction of the structural performance and into the evolution of the prediction of the structural performance. So we are trying, this is a schematic, but we developed some real case design examples. And I will tell you, we have developed a MOOC lecture on this, and I will tell you at the end where you can find this MOOC lecture. Well, if you plot, for example, any structural performance over time, and you have a reinforced concrete, you will have a curve like the gray one. You start with a certain performance, then you have a slow decay, but then at a certain point, you have carbonation or chloride induction corrosion. When the corrosion starts, your performance starts decreasing very fast. So at a certain point, when you will reach a level of performance that you will no longer accept because it's too close to the demand, you will say, this is the end of my service life. Well, obviously, using higher performance materials, we will be able not only to increase the performance at time 0, but also to govern the degradation over time of this performance. But what does it mean, end of service life? Is this truly the end of the life of the structure, or shall we start thinking in a cradle-to-cradle approach? So we also addressed the issue of recycling these materials. And it's an interesting topic because these materials have a lot of cement and low water. They contain a lot of anhydrated cement. So if you crush and recycle it, the cement will be able to react once more. And so you can see these initial results. We have results just at a very early age for the strength. At 7 days, for example, the reference mix had a concrete strength of 80 megapascal. But if we replace 5% of the sand with 50% recycled material, we get the same strength. And if we replace the natural sand totally with recycled material, we have an even higher strength, probably because we introduced in the recycled material additional cement content, which is able to further react. This is an interesting work that we are performing together with University of Malta and University of Valencia in Spain. Well, summing up, we addressed 5 of the 6 keywords of Calvino: lightness, quickness, exactitude, visibility, and multiplicity. What about the last one? Well, the first thing that you may ask for, everybody asks for, is the cost. How much this material cost? And we are used to speak and think of cost per cubic meter. But we have to think beyond of this. With our materials, we do not make 1 meter side cubes. We make structures. So we should say, how does a cubic meter of material, what does it give me back in terms of structural applications? So this is a picture of casting this material on the construction site of a plant. This was a site visit that we made a few weeks before the lockdown in Italy. I did this visit with my colleague, Professor Bamonte, and Salam did a visit with Dr. Lomonte, another colleague working in this project. We went there to supervise works during the construction. And this is the pilot built. You can see me on the corner. This is a 20-meter long by about 7-meter wide. You can see on the bottom the original solution, in the middle the 6-centimeter stick solution, and this is the precast. You can see the slabs and some of the formworks for the columns. And you can see in these insets on the top left, the 10 centimeters original reinforced concrete wall, the 6-centimeter stick UHDC, and the 3-centimeter stick, just to show you that these are not numbers, this is the reality. And we are going, as soon as we will be able to go back to go back to the site, we are going to start validating the project, filling it with water and monitoring the performance. This is another picture of another basin that we built in the same site. You can see how does it flow in formwork. Is the corner which is marked here in red. Well, actually, since this material is highly fluid, one of the problems was also designing the formworks to static pressure and to understand how fast was the development of the strength. This is a tensile test made after half an hour with a specific setup that we developed, and we correlated the results to the rheology of the material and to the yield stress buildup of this material. Some other images. This is another pilot of our project made by our partner, Spanish partner, RDC, Research and Development Concrete. And this is a picture of our consortium group. We had this meeting at the end of February, really immediately before the lockdown in Italy and Spain. This is a raft for mussel farming. You can see in this scheme on the top left, how will it work? In green, you can see the floaters. This is the structure that you can see in the picture here. And you can see the mussels and the seafood which is farmed there. This is another pilot made by another Spanish partner, Rover Maritime Group, in collaboration with University of Valencia. It's a floater of a wind tower. These are some renderings, but the pilot, when I visited them, was going to be installed in the lab. This is the floating pontoon in Ireland, some pictures of the casting. The pilot is ready and is ready to be floated also. And these are some pictures of the water tower that we are retrofitting. You can see the initial retrofitting of the column that started, and there the work is continuing too slowly because of the restriction due to COVID. Well, summing up to the conclusions, we have tried to show you the main findings of the project. As I said before, we had summarized all these results in a MOOC, which will be made available starting May 11, and you can see here the details on where to sign up for this MOOC. But if you have any question, you can email me or you can contact Salam, and we will be happy to share them with you. And I want to thank you with these group pictures of all of us during our meetings in different parts of Europe. This is a dinner picture of our last meeting in Valencia at the end of February. And I am also very proud to show here, you can recognize in the picture Salam in left, our research group at Politecnico di Milano in front of our main building. And thank you for attending this talk. Shukran Yazilan.
Shukran, Professor Feyerabend. Thank you. Thank you for your informative presentation. And again, I would convey the message from the President of the University of Al-Qadisiyah and the Dean of the College of Engineering in the University of Al-Qadisiyah. I will literally convey the message to you. They say we express our thanks and appreciation to Professor Feyerabend for this valuable information and presentation. And we hope that this participation will be repeated in the upcoming international conferences, cooperation in the field of scientific research, supervision, and discussion of graduate students here. Welcome, Professor Bas.
Thank you very much for a very interesting presentation. Dear Professor, I'd like to ask this question. In the samples used alumina nanofiber, did you observe it as a self-healing promoter?
Well, this material is autogenously self-healing because of the high content of cement and low content of water. So there is a lot of long-term delayed hydration. The alumina nanofibers, what they did, we observed, is that first of all, they improved multiple cracking in the sense that you have more cracks and they are narrower. So a narrower crack is more easy to be healed. The other thing is that, in a sense, they also work as seeds for the delayed hydration. So they are not the main responsible for self-healing, but they improve it.
Okay, thank you.
Yeah.
Next question. You can write in the drop box, in the chat box, if you have any question. Even if Arabic, I will translate it to the professor. Okay, we have this. This is thank you.
Okay. Okay, may I ask other question? If there's...
Yeah, you're welcome, Professor.
What is the role of model for limit and surface status design for durability?
Well, we are currently working on that. As a matter of fact, what we are, and this will be a little bit the topic of Salam PhD thesis. What we have realized is that when you design these structures and you design so thin, the problem will shift from ultimately by structure, whereas the serviceability is something that the structure experiences. So we are currently working on implementing reliable crack opening calculation models in order to be able to predict the serviceability and to incorporate into the serviceability model the durability as well. For example, we want to try to quantify the reliability of healing of a crack of a certain width in order to incorporate the self-healing into the design. It's something quite challenging, which we are currently working on, also with the aid of sophisticated multi-scale numerical models on which, together with my colleague, Professor Di Luzio, we are supervising another PhD student who is working on the project.
Okay, thank you.
Thank you, Professor. Any other question, please? Okay, Dr. Maha Al-Sudani. You can write.
I think Dr. Adnan has a question. Dr. Adnan.
Okay, Dr. Maha Al-Sudani, we will give you, you can speak.
Can I ask my question? Sorry, Dr. Salam.
Okay, Dr.
Okay, Professor.
Yes, this is Ali Najatiya from University of Kufa. Thank you, Professor, for this really interested presentation. My question is about the performance of this new concrete. You showed us a curve, but it was very fast. The deformability of this three types of concrete, which is, I think, a curve between the moment and the rotation and the horizontal axis. Yeah.
No, it's time, actually. No, that was a schematic graph. It was not a true graph. Yeah.
Ah, yeah. So the horizontal axis is the time, not the rotation.
Is the time. Yeah.
Oh, the time. Yes. My question is about the three types. You showed us that there are more deformation in the concrete, which will be used with fibers. So would you please add more information about this point?
Well, actually, the thing is that these materials, well, they have a large deformation capacity, whereas regular concrete cracks, and that's it. And you need to have the ordinary reinforcement after that. These materials, because of the fibers, they have a higher deformation capacity in tension. So the thing is that the key idea is that we have to exploit that, because this higher deformation capacity also means that they are much tolerant to damage. And so you can really optimize the design of your structure.
Yes, yeah, thank you. Thank you very much.
Next question, Dr. Adnan.
Hello.
Yeah, we can hear you, Dr. Adnan. You can speak.
Okay, thank you very much for this valuable presentation. I have three questions, please. The first one regarding with the easy with which we can about the application of this material for the repairing the reinforced concrete members. And the second question, please, about can we classify this material as ECC? That means engineering cementitious composition, engineering composition cementitious material. And the third question about the aspect ratio for the steel fiber used in this material.
Okay, so let's start from the latter, which is easier. Well, the fibers were 20 millimeters long and the diameter was 0.22 millimeters. So the aspect ratio is about 90.
Yes.
The material is actually an ECC. The concept may be a little bit different because ECC, you know, have a low tensile strength and high deformation capacity, whereas these materials have both high tensile strength and high deformation capacity. But in a sense, the behavior is very similar. They are strain hardening in tension, and that is the concept. About the use for retrofitting, yes, they are ideal candidate, and we are using them also for retrofitting, and we have used them also in other projects. Well, actually, it's very, you have to be very careful when casting, because the casting process, the mixing process, even the mixing is has to be very well taken care of. And well, for the application, depends on what you want to retrofit. For example, in the water tower that I show it to you, I may probably try to go back to a picture of it. Let me, okay, here it is. Let me see if I can retrofitting.
Okay, thank you.
And yeah, you know, I also can see the last pictures looking at cyclic behavior. Yes, well, actually, there are studies on the cyclic behavior of the material. We use it, for example, them in retrofitting shear walls under cyclic loadings, and they performed excellently. And we will monitor the pilot, because all the pilots which will be in the sea, they will be subjected to the cyclic action of the waves. So we will monitor their performance under cyclic loadings, yes.
Okay, thank you very much.
Okay, we can take one more question. Dr. Haidar Jilawi. Okay, we will take Dr. Maha, I think. And that's it. Okay. So thank you, Professor Ferrara, for
It has been
your,
truly my pleasure to
yeah,
be with you tonight. Thank you, really.
and thank you very much.
I was
On
really
behalf
very
of-
happy.
Yeah,
Thank you
behalf
very
of
much.
all the
Bye-bye.
audience, I will thank you. Bye. Ciao. Thank you.
Good night.
Good
Bye-bye.
night. Bye. السيدات والسادة الحضور، نشكر حضوركم جميعا، ونحب نذكر بأنه الورشة كانت من قبل قسم هندسة الطرق والنقل في كلية الهندسة جامعة القادسية تحت عنوان تصميم الخرسانة المسلحة الديمومة في ظروف بيئية قاسية. اللي عنده أكثر سؤال يقدر يعوفنا السؤال بالشات بوكس، واحنا نقدر نجاوبه، هو السؤال والايميل، ونقدر نرجع الجواب ان شاء الله. شكرا جزيلا جميعا.
السيدات والسادة الحضور، نشكركم جميعا لحضوركم في هذه الندوة لهذا اليوم. أي أسئلة الرجاء الكتابة على الشات وسوف نجيبكم عليها. نتقدم بالشكر الجزيل للسيد رئيس جامعة القادسية والسيد عميد كلية الهندسة لدعمهم هكذا نشاطات، ونتمنى التوفيق للجميع. شكرا جزيلا.
السلام عليكم اخوان. رابط الحضور نزلناه، اذا ما يعمل عندكم ما تقدرون تستنسخوا باعتبار انه الزوم جديد تصير حالات ايرور بي، فنزلت لكم مستند على شكل تكست ونزلت لكم كيو ار تقدرون تاخذون الصوره بالكاميرا وتسوون سيرش على الرابط عن طريق الكيو ار. راح اعيد هسه ارسالها امامكم.